diagram. How does it do it? Because it changes the relation between the conformal time and the proper time. It does it by putting in an exponential there, which makes a very big difference, obviously. And so what the effect of inflation is, it makes no difference to any time later than the end of inflation. So if that's the end of inflation, it makes no difference to anything after that. In particular, inflation does not change the visual horizon. It has no effect on the visual horizon. What it changes is the causal horizon by shifting down the Big Bang from here to way, way down, something like this. And that means that this part light cone here and this past light cone here now have a large area of overlap. And that means you can have some common mechanism which affects both of them. And so, roughly speaking, in a diagrammatic way, this is how inflation solves the causal problem, which has come to be called the horizon problem. Okay, these causal diagrams really do help one to understand very, very carefully how causality works in these Robertson-Walker models. I must emphasize again, the physical distances here, the physical distances are the actual distance you would measure will be scaled by the scale factor times r, and that is going to 0. So remember, the actual light cone is collapsing to a point here. So what is causally a hyperplane is, in terms of metric distances, a point. And people get very confused about that. The causal behavior and the physical behavior in terms of the way distances behave are completely different because they are scaled by a of t, which goes to 0. So the distance goes to 0 even as the causal size remains finite. What you need to remember, the singularity itself is not a part of space-time. Space-time is everything future. That t is naught is the boundary. It is not in space-time because at t is naught, the metric has broken down. So this is the boundary of space-time. It is not in the space-time. Okay, well, the upshot of all of this is that the part of the universe we can see is a very small part of the whole universe, and this has important implications. For example, chaotic inflation cannot be tested observationally. Because in chaotic inflation, somewhere way out here, there's a sort of a huge wall or something, and the other side there's a different Friedman-Robertson-Walker model from over here. In chaotic inflation, there are these huge sections of Friedman-Robertson-Walker models with different characteristics. But the point is, this other one is way out there beyond the visual horizon. That means no information of any kind comes to us from that other domain out there. That means that the hypothetical existence of those domains cannot be tested by any observational test. SALT will not tell you if we live in a chaotic inflationary universe or not. It cannot do it because these regions are way outside. And in terms of these kinds of limits, I want to sort of finish off this little bit with just a comment. The ultimate of this lack of causal connectivity is in what has become to be called multiverses. And I could give you a whole lecture on this, but I won't. But the idea that our universe is not the only universe, that there are thousands, millions, even people say an infinite number of other universes out there apart from our own universe. Now, people peddling this idea include Martin Rees, they include Max Tegmark, they actually even include Steve Weinberg. And what people want this multiverse for, all of these other family of universes, is so that you can apply statistics to cosmology. And when you've only got one universe, you can't apply statistics to cosmology because there's only this one thing sitting there. But if you've got this ensemble of millions and millions, maybe an infinite number of universes, wow, now we can apply statistics. And that's what Weinberg and Tegmark and Rees and other people would like to do. So maybe, apart from what we're seeing here, somewhere over here, totally disconnected, there's some more universes, there are other light cones, there's other expanding domains, with no causal connection of any kind whatever, because these are completely discrete space-times. Well, together with my colleague Bill Sturger, we are fighting a little battle with Martin and the others to say, is this science or is this metaphysics? Because if you have a hypothesis like this, in which there isn't even the faintest chance of obtaining any kind of observational evidence, in my view, you are talking metaphysics, and you are not talking science. These various papers by Martin and Tegmark and so on try to say that this is a part of physics rather than metaphysics, and this is a very interesting area of current debate. Watch this space. There's going to be a lot of action in this space between the people who are pushing the idea of a multiverse and the people who are saying that this is metaphysics. Okay, now, I've done as much as I'm going to do about the Robertson-Walker models today, the standard models. I'm going to finish off today by a very, very brief set of comments on other universes, which I've spent a lot of time on because I really enjoy them. As I said this afternoon, in the popular lecture, I will be talking about the concordance model with some criticisms, and then tomorrow, I will be talking about local physics in the expanding universe, which is an interesting topic, quite different from what I've been doing now. So the remainder of what I want to do in this talk is just very briefly to talk about other models. So the universe, most of cosmology is based on the Robertson-Walker models. But is the universe Robertson-Walker? Well, I've given you evidence that it is Robertson-Walker within our past light cone down to the surface of last scattering. But at very much earlier times, was it Robertson-Walker? Will it remain Robertson-Walker model at very much later times? Some really interesting work has been done looking at this using the basis of dynamical systems method in cosmology, and a nice book on this by myself and John Wainwright summarizes a whole lot of this work. And I'll give you a brief summary and then say some comments about it. There exist universe models which are observationally indistinguishable from a Robertson-Walker model that are quite different at early and late times. In other words, even if this patch of the universe that we can see from today down to the surface of last scattering is Robertson-Walker-like, there are universe models which are very, very close in that domain, but which are completely different at very much earlier and very much later times. And I'll illustrate this by another dynamical systems diagram coming from the study of inhomogeneous and anisotropic models. This is actually a diagram that comes from Bianchi 2 universes. And what you have is one anisotropy parameter this way and one anisotropy parameter this way. These are what are called the Kasner ring Kasner models. These are vacuum models, which are very well understood. This is the Friedmann-Lemaitre model, and obviously I don't have time to explain all the variables. Basically what I'm saying is this is the isotropic flat Friedmann-Lemaitre-Robertson-Walker model. This is a very anisotropic empty universe. This is a very anisotropic empty universe. This is the vacuum boundary, and that is a plane wave state, which is the asymptotic state at very late times. Now, this is for Bianchi 2 universes. F is a fixed point. The Robertson-Walker model is a fixed point, but it's a hyperbolic fixed point. And you get an evolution here from the Kasner model to the Robertson-Walker. You get an evolution there from Kasner to Robertson-Walker. The generic evolution is to go around and end up asymptotic to a plane wave state up there. Now, hyperbolic fixed points have a very interesting property. As you come along here, it's a fixed point, so the arrow pointing along there gets smaller and smaller and smaller, and it goes to zero in the limit. In fact, as you know from the way hyperbolic points work, it takes an infinite time to travel along there. You never actually reach that point. You get closer and closer, you never reach it. Well, what that means is, if you take this curve here, the tangent vector is very large there, it gets smaller and smaller, it gets very small here, it gets larger there. That means that as you travel along here, you travel very fast, you stay a very long time there, you hover there, and then you rush off and approach that space asymptotic state up there. So in this phase plane analysis, if I choose curves that go closer here, they spend longer and longer here, and they are closer and closer to the Robertson-Walker model there. They were completely different to start with, and they're completely different to end with. You can choose a time as long as you like. And there is an infinite number of curves. There's an open interval of curves that spend greater than that length of time, closer than epsilon, to that Robertson-Walker model. In other words, choose a model as close as you like to Robertson-Walker, choose a time as large as you like, and I will find you a one-parameter set of models which start off in a completely anisotropic way, they end up in a completely anisotropic way, and they are indistinguishable observationally from a Robertson-Walker model, because for all of that observational time, they are closer to Robertson-Walker than you can distinguish by any observational measurement. And so this is what we call intermediate isotropization, and this is just to show you that you can actually find out quite fun things by looking at these phase planes for anisotropic and inhomogeneous universe models. If you believe in generality, you see, some people, as I say, believe in speciality and some in generality. If you believe in generality, you have to make the following deduction. In the real universe, this is one mode of inhomogeneity. It's a spatially inhomogeneous mode of inhomogeneity. If you believe our universe is a general universe which has then been isotropized by a process like inflation, you have to say that this anisotropic mode is there. It is non-zero. And if it is non-zero, it takes over at early times and at late times. And the universe may be like a Robertson-Walker model for quite a long time, but it's not like a Robertson-Walker model near the initial singularity, and it won't be like a Robertson-Walker model in the far future. So this is just the kind of thing which is quite interesting to look at these models. And the final thing I will...
Growing mode in the far future if the universe remains cosmological constant down?
Oh, sorry. Very good point. This is for vanishing cosmological constant. Sorry. If the cosmological constant is non-zero, then it'll be different. Thank you. Yes. Yes, I'm still getting used to the idea of the cosmological constant.
5 years now.
The final thing I'm going to give you a diagram which shows you how anisotropic and inhomogeneous models work. And what this is, it's a diagram of how symmetries work. And for symmetries, there are two basically important kind of things. When you have a symmetry, then there's a surface in which everything is the same at every point, because there's an isometry group which moves you around on that surface. Now, the dimension of what we call the invariant variety is then S, and that is the surface in which the homogeneity acts. Now, in a standard Robertson-Walker model, you can have four-dimensional surface of homogeneity. Everything is the same in the whole of space-time. That is S's form. You can have S's 3 spatially homogeneous models like the Robertson-Walker models. That is S is 3. You can have S's 2 inhomogeneous models in which the surface of homogeneity is two-dimensional, like spherically symmetric star models. So S is the scale of the surface of homogeneity, the size. There's a second very important thing. Around each point, there is an isotropy group in general. The isotropy group moves directions around in the sky, leaving everything invariant, and that's what I call Q. And there are three possibilities in general relativity. The isotropy group in a non-empty Robertson, in non-empty universes, I must emphasize this, in non-empty universes, the dimension of the isotropy group cannot be bigger than 3, because your 4-velocity vector gives you a preferred direction, and all the symmetries take place in the orthogonal 3 space. That's a maximum 3. There isn't any 2-dimensional one. Isotropy group can be one-dimensional, which is the case of local rotational symmetry. There's an axis, and everything is the same around that axis, but it can vary along the axis, and you can be anisotropic. And so this dimension is S, this dimension is Q, and then the group dimension R is S plus Q. And you can classify models according to these symmetries. Now, for the space-time homogeneous, you have the Einstein static universe, which is no good as a model of the universe today, but it's an interesting asymptotic state. You have the Gödel universe when it's rotationally symmetric, and there's a whole family of anisotropic models which are known and are not of particular interest cosmologically. These are the ones which are space-time homogeneous. The spatially homogeneous ones, the Robertson-Walker model is the one that's